attack a little optimization problem. Say you have a function here only in 2D, so it's a function of x and y that produces some strange contour image here. So you can think of it as a terrain, for instance. So we have a very high peak here, and a smaller one here, and another one here, and so on. So the optimization process now goes as follows. Find the biggest peak. So that's an optimization problem. And of course in 2D, no problem. You just print out this ISO plot, and then you can see it with one eye closed. But what about an n-dimensional problem? How do you solve it? That's actually a topic of its own, optimization. It's not necessarily that easy. To solve this one, you can think of sort of paratroopers that you just throw out randomly from an airplane, and then tell each soldier to walk up. As long as you walk up, you continue walking. When you reach a place where you can't determine direction up anymore, you stop. And optimization actually uses such random algorithms to find a good optimum. And here, of course, no problem. We don't have that many peaks, so yes, they find it. And also here you risk that initially, if he finds a position where, say, you have a saddle point curved this way and this way, then it can be hard to find the direction up mathematically. So, and also if it's totally flat, you can't go anywhere. So, not so easy necessarily. But using these ideas here, walking the direction where it is steepest to find then a local optimum at least, that's pretty much a philosophy within optimization. What do we need optimization for? We are solving an equation system that is just a whole bunch of linear algebraic equations. We just want to solve them fast. Well, we are going to switch our problem into just an optimization problem, or actually a minimalization problem. And the way we do this is find the corresponding functional to our equation system. So we had initially an equation system reading matrix A multiplied with the unknown B equal unknown x, sorry, equal the right hand side little b. X and b being vectors, A is a total coefficient matrix. Then we construct a functional, as we call it, f of x, looking something like this. And then we are now going to seek where is this function smallest, finding the minimum of that function as a function of the position x, and x here being a vector with all your unknowns. So this is an n-dimensional problem. Of course you can't plot it. If you had two equations and two unknowns, of course not a problem, but you have 10,000 unknowns, 100,000 unknowns, then this is a 100,000 dimensional problem. Not so easy. Let's see what this f function, where he comes into our equation system. Well, finding the minima, that means the gradient of this function in any direction, meaning derivative with any of these x's, should then be 0. Then you have a minima or a maxima. So if you write the derivative here on the matrix form of this strange f function that we just invented, it will then in general look something like this. And if this A matrix is symmetric, which it normally will be, then you see this f derivative is reduced to our initial equation system. In other words, if you can find the place where all these derivatives are zero, you have solved the problem. So that's the philosophy behind these Kirillov methods. Minimize this functional f instead of solving this equation directly. That's the philosophy. Again, talking about the residual, here defined maybe the other way around as we did it with Muntigditz. So it's just a minus, just a definition anyway, so don't worry about it. And then you see from the equation we just had, this derivative equals minus this residual. The gradient of f, now that will be the direction sort of upwards in the terrain, if you can think in terms of a 2D problem. So we should then walk in this direction to hopefully finding the minima or maxima. And the direction is then given by actually the residual vector. Proofs, yeah, you can have a look if you want, but yes, they will be true. Now, how does such a function look like? Well, here it's drawn in the case where you have just two unknowns, x1 and x2, and then you draw this f function, how it looks. And he will always sort of have one minimum. And when you have n unknowns, you can't really draw it anymore, but you can still think in terms of this geometry. So it will have sort of a bottom point, which we then are seeking. So the simplest method now, sort of the other way, throwing out paratroopers, making them walk up. Now they have to walk down, find the lowest point. It's a minimalization problem. So we just use then the method of steepest descent, as we call it. You walk down where it is steepest to hopefully find the position of the bottom as fast as possible. And if you're up on the mountain and have to go down in the valley, this sounds like a good idea, right? Well, actually it's a bad idea. It's not the fastest way down from the mountain. That's where the water is running. But if you have been mountain climbing a little bit, you should know when you go up or down, you should never follow the small rivers and small creeks. They are way too steep. And in the end, it's not the fastest way down. Well, if you stumble, then maybe it's fast, but no, that's not the point here. I'll show you. But the philosophy behind it is fairly easy, because if you're standing at a point, you can calculate the local gradient then of our functional f, and then from the equation system, minus f derivative, well, that's equal the residual, which can easily be found at that location, x1, or x for all the different x's here. And when you know the direction, the f gradient, then you can find a much better x by just walking some distance alpha, just a number, how long you should walk in this direction. So here you sort of have the recipe already. You start with a guess point, find the local derivative, which is the same as the minus residual, and then we walk in this direction. Now the question is, how far should we go? So we have to find this alpha. And the example, it's taken from this this introduction to the conjugate gradient method, made painless by this student. He had two equations, two unknown example, so I think it should be here somewhere. Here we have it. So this is the problem. You have two equations with two unknown, x1 and x2. Graphically, the answer should be here, for x1 and x2. So this is one way to solve such a problem. You can do it graphically. Of course, here no problem to solve this equation system directly, but remember we are working actually with an n equation system, so can't do it like that in practice. But for 2, yeah, that is quite okay. And given this these equations, it's not a problem then to calculate how does this f function actually looks like. Well, it will look something like this. And if you plot it, the contour, here should then look something like this. And this was the initial guessing point. Yeah, well, maybe we shouldn't plot it like that. Let's try it a little better. Just crush it and then figure contour f axis equal. It should be better. Yeah. Now it's more correct. So the contour plot, that's the f function. The minimum here somewhere. And then we start first initial guess here. So now the theory goes as follows. First, find the residual at that point. That's not a problem. And then you use the residual, minus the residual is the downward gradient at that point. So you will get a direction perpendicular to the isolines. So he will show you walk this way. And then it was the question, how far should you go? How big step should you take? Well, the step should be as long as you go down. Then you should continue walking in this direction. But here, you should stop. Because if you continue, you start to go up again. So this alpha, we have to calculate it as long as you go down in that direction. So that is the job with the alpha. And to find it, it's a little tedious math here, so I won't go going through it. But you will have a very cute matrix expression for it here. So it involves a little matrix multiplications, but no big deal. That doesn't cost much on a computer, so it can easily be found. Remember now, alpha, you have one alpha in each direction. So alpha is a vector just as long as all your unknowns. Having this alpha, we can then continue our problem by now doing the same. Now we are standing here. Then find the residual here, use that one as the new direction, which then should be perpendicular to your isolines here, and walk as long as you are going down, and then you stop when you start going up again. Another alpha here, and so you continue until you finally reach the bottom. And here, I think I said 10 to the power minus 6. You need 23 or something iterations. And then you can do it again and again and again, starting with different positions. So yes, this method works. And I mean, the algorithm here is very, very easy. Not that many steps. That has to be calculated. But it's not so efficient that we would like. But the entire source code is 3 lines. Well, we need 4 all around it. But this is the entire algorithm. Very easy. Start with an initial point, xi. Find the residual. Then you know the direction you should go in. Find how long step you should take. Okay, and then you can update your position to a smarter one. And just repeat this over and over and over again. So yes, this method works alone. Very short, but not so efficient. If you look at, I have to crash in first. If you look at the way he works, you will see the first step perpendicular to this also occurs here, and then 90 degrees, more or less, and then 90 degrees again, meaning this direction and this direction has been used twice. That's a waste of effort, isn't it? So you see, you use the same directions many, many times here actually before you hit the center, before you hit the bullseye. So this is a waste of effort, yes. It would be very nice if we could do it more efficient here. And of course, if this original problem had been, these ISO lines had been perfect circles, that would be very, very nice. Then you would have hit bullseye with the first step. No problem. So how to make these ISO lines in general, for a general problem, how to make them circles? Now we are talking conjugate directions. That's the whole point. For a real problem, you should imagine this functional f. The layout of it will be a very steep, sort of a canyon, and very long and very narrow. So that's sort of how he would feel in practice for a numerical solver. So what you're actually doing here with the steepest descent, you're sort of using a blindfold, tumbling your way in the dark down a canyon and still going down, and you're sort of banging from wall to wall to finally get to the bottom. So very inefficient. Conjugate gradient should sort of look longer ahead. So let's see how this one is done. Of course, very cute here is the program. The codes are extremely small. And also the memory requirements here shouldn't be too big, unless you store this A matrix in full. That's not funny at all, but because I mean mainly consists of zeros. I will look at that later. But here, no, you don't have to store it in full. I'll show you how that is when it's done later. Because here we have matrix operations, so we're going to need this coefficient matrix A, regardless if it's mostly filled with zeros. Yeah, sort of the same text here, as I've said. The second part. Starts with the same. Original problem is now to be solved by minimizing this corresponding functional, as we call it. And steepest descent, yes, it works, but it's too slow. So now we want to change this one, this algorithm a little bit. Here you have the steepest descent. But now we want to change the directions of how we tend to go. Here now is an example for the steepest descent, solving a Poisson problem. So you can have a look at it if you like. Steepest descent alone, I would say, is not as fast as an SOR with a good omega. So it's more like Gauss-Seidel iterations. A little bit more efficient, but not much. So fairly easy to do the programming. Here a lot of do loops, Fortran notation. Of course this can be programmed now directly with matrix notation. You don't have to use loops at all. So then it's a very compact computer code. So now to try to make it more efficient. Steepest descent, use the same direction over and over and over again. So to avoid it, we will go in what's called the A-orthogonal direction. Now what is A-orthogonal? Well, that is when we have transformed this long elongated canyon into circles, circular terrain. Should look something like this. Then these vectors will be 90 degree if it was a circle, and here, using now steepest descent on this terrain, if you start anywhere, finding the direction to go, perpendicular, and then go as long as you go down, you hit bullseye every time. First step. So that is what we are aiming for. Sadly, we have it on this form. It's very elongated and can be actually in any direction here. But these vectors that are indicated here, they are actually A-orthogonal, 90 degree on each other. So these has been constructed with a matrix formulation, which then looks something like, yeah, even try to draw it in 3D, not so easy to see. You have two vectors, D1 and D2, they will be A-orthogonal with respect to this coefficient matrix A if this product is 0. So we use this definition to calculate now the new direction. And then the philosophy will be as follows. Of course, to hit bullseye every time on the first step, that is a dream. It might be true for two equations with two unknown, but for a problem with n unknowns, no, you have to do it many times. You have to do an iteration process. But to use A-orthogonal directions, you sort of ensure that you will never use the same direction twice. That's the idea. So it should be much more efficient. So now the calculation will be a little bit more tricky. The philosophy behind it is of course the same. So to solve this one, minimize the corresponding functional. So we start sort of the first step. That will be a steepest descent step. We have to begin this procedure here to have an initial walking direction. When we have that, we seek now the A-orthogonal direction for the next step. So we will sort of have to find this A-orthogonal direction, which then will switch a little bit of the logic here. Not so easy to see it here, but you have another route where you then use this definition for the A-orthogonal directions, a new walking direction instead of the residual direction directly. And then it can be seen then the following algorithm. So the first step should then be an ordinary steepest descent step the first time. You have guessed an initial point, can find a residual, and here we also call it a D direction then. First alpha as before, and then we update as before. So now we have the second point, you might say, of the steepest descent method. Let's see, is it here? Yeah, well, again I should use x is equal. Same geometry, same problem, and same initial starting point. Start here, and now take an ordinary steepest descent step, just the first one. And now, the steepest descent would say you have to go in this direction, but now we are going to adjust this direction to something more sensible. That's the whole point. Oops, that was a little too much. From this new position, you calculate the new residual, calculate beta as the sort of conjugated direction and the new length of the step, now written in this form. So the algorithm is not much bigger, a couple of sentences in addition, that's all. So of course a little bit more matrix multiplication here, but absolutely worth the effort. So if you now look at the problem, take the second step and you hit the bullseye directly. Because this was two equations with two unknowns. With n equations, well, you have to iterate more times than two, of course. But yes, this is much more efficient. You can start wherever you want, and it finds the solution every time in 2 steps. You have to take the first initial step as a steepest descent step. And that's it. That's the entire theory that you have to think about so far. Now, if you do this in practice, it will be quite obvious for a real problem, many thousands unknowns, millions unknowns. Yes, this will work, but it's going to take some time to find a solution. You have to iterate many times still. Of course, here I would say this, what do you call it, a pure conjugate gradient method. Yeah, he will balance and be more faster, should be more faster than an SOR with a good omega. But we can improve him even further. That's a possibility. Yeah. The conjugate gradient direction. So we have now a whole family of different variants of the conjugate gradients, and they use some sort of a preconditioner, which will make it much more efficient. And you have different ways then to solve it. And all these routines you can find in MATLAB, find them on the net, find subroutines for them, cute little subroutines. Some of these might be a little bit advanced, but a pure conjugate gradient, that's very, very easy to program yourself if necessary. And yes, this problem also has been expanded to solve even if your coefficient matrix A is unsymmetric. So there's a little bit more math than behind this Krylov methods, but I won't go through it at all. But these methods can handle even that. the part that really speeds up a conjugate gradient, that makes it really efficient, that is a preconditioning. We try to improve the equation system that we had initially, AX equals B, to make it more suitable for the conjugate gradient method. So, philosophy then, we multiply our equation system with a very simple M inverse matrix on both sides. Now, of course, if this M inverse, if he was equal to A inverse, well then we have solved the problem here. But that's not the point, because that will be a direct method, finding A inverse. Now remember, the coefficient matrix, he is very sparse, mostly zeros. But A inverse is going to be a full matrix. So if you have 1 million unknowns, A matrix is going to be a 1 million by 1 million matrix. You're going to blow any memory in any computer. Even if you add all the computers together, you still will blow the memory. So that's not possible using a direct method for a big problem. But if we at least could create or design a matrix here which will make this product closer to A inverse, of course it will be easier to solve the problem. So that's sort of the philosophy behind this preconditioning. So we should do some tricks here first, and then this conjugate gradient method will be much more efficient, much faster. So just some simple examples here of some preconditioning methods. Jacobi, just using the diagonal of the original matrix A, but it doesn't really help much. So that won't really speed up the process at all. This one is quite popular. It's an incomplete lower upper decomposition then of your original coefficient matrix A, here to be used as a preconditioner. Here you have to be careful, because you can get these lower upper triangles then of the A inverse matrix, that's the aim here. You can make them very good, so good that you are very close to finding A inverse, but then you blow the memory. So if you really want this preconditioner to do a good job, it's a memory price. So you have to make the balance here. How well should these lower upper matrices be to A inverse? Careful. Be careful. So I wanted to show you a little bit about how to use this. Here I have programmed our sort of a classical test case. I think it's just the Laplace equation here. So now I make it a very simple problem, a 4x4 problem. And then I construct my coefficient matrix A. Here it's done rather straightforward, a little stupid, but never mind. So if I now run this one, and then crash him, I should have a matrix A. Ah, my mistake, he made it 16 by 16. Okay, we can still see it, I guess. So the matrix starts here, you have the diagonal of -4. So this is typically from the Laplace operator. You will have -4 on the diagonal, and then you will have 1 for the neighbors, but you'll have another one here, and then we should have a third one as well. But typically the first unknowns that you have, they have a boundary also, so that will be a part of the boundary value, which is known, and then typically that will belong now to the right-hand side in your equation system. That will be in the B vector. So, but I mean, this will be the standard layout for the Laplace operator in 2D. One diagonal, and then you have 4 different bands with just ones. And you see the rest is in 0. All the way down to the end. So if I now write whose, you see my matrix A, it's 16 by 16, and sadly then mostly zeros. So my right hand side, that's just 16 by 1. And I don't think -104. Okay, so it's a Poisson equation then. He's not 0, he is a constant. I think it's double derivative equal to -1 or something. Never mind that. My point here is this A matrix can be a little bit too big. So if we now increase our problem, say 40, and crash, and whose. So I have a 40 by 40 problem. So then it should be a 1600, and then the coefficient matrix will be a 1600 by 1600 nodes. And you see the memory is really getting there. And of course, I don't remember how much memory I have on this one. Let's try it. 100. Ah, he survived, I think. Ah. How big is it? 1, 2, 3, 1, 2, 3, 1, 2, 3. Closing in on the gigabyte. So of course very easy to blow the memory. 100 by 100, that's really not a big problem. Even 400 by 400, that's not a big one. But 400 here, I blow the memory. So you can't really do this. So what do we do? Well, you have a good trick. Yeah, I can show it to you if I go back to the simplest one. 4 by 4 unknowns. That's 16. And my A matrix now is a matrix looking something like this. Then you don't store all the zeros. Store only elements in the matrix that is different from zeros. How do you do that? In MATLAB, A equals sparse. Sparse of A. Then you have it on this form. These are the indexes to the location in the A matrix where you have something different from 0. The rest is not stored since they are 0. So the matrix A is still a 16 by 16, but it doesn't use that much space anymore. And I have an attribute for it, is sparse. But you can use it in the rest of the program as if it was just an ordinary full matrix. So you create them as sparse. And now it should be possible to go to 400. Maybe not 400. No, of course not, because I have it here. My mistake. So instead of writing A equals zeros to set up space, I write sparse. And then it works. I can crash it and write whose. And now you can see, you can handle now how many 160,000 unknowns, and A is now 160,000 by 160,000 matrix, coefficient matrix. That he hardly needs any space at all with this attribute.
Will the matrix routines be slower because it's stored in a like slightly more difficult format?
No. Remember, in practice, when you do some matrix multiplications, operations, whatever, in a computer, he's going to use a pointer anyway to find, okay, I need this element now to put it in the CPU, multiply with this number, also in the CPU, and do the multiplication. So that will sort of be a pointer. Well, this sparse technique, he has sort of the pointers in one end already. So no, it doesn't take much. So using sparse as attributes in MATLAB or in other program languages, you also find this sparse guaranteed. That's a really neat trick. And then you just define it as a sparse matrix, and then you can forget about the sparse thing in the rest of the program. Use it as ordinary. Very easy. Any other questions? Let's see how big we can make it. 40,000 by 40,000.
If it's not slower, why isn't it just a default format for matrix?
Because I think a lot of people like to print out the matrix.
Well, I guess you could change the printout function even though it's
Yeah,
sparse.
yeah, you could. That's true. That's true. Ah, this one here, I think I blow him. Oh yeah, he has trouble. And this is a dangerous thing with MATLAB and also other languages. When you start squeezing the memory or pushing the limits, you are messing up the operative systems in the computer, so you have to find the power button and reboot the entire machine. That happens frequently. Normally, you should make him stop with a Control-C, but you see, no. So the computer takes a break, and I think we also take a break.